All right, guys, today we're going to talk about chapter 2, okay? So I'm going to go ahead and throw this slideshow up. We're looking at atoms, molecules, and ions, all right? So here we go. Hopefully, just like last week's lecture, this will be a lot of review. I am going to move through it kind of quickly. Remember, use the Cornell note system, all right, to take notes as you progress through this. Hopefully, you've already read the chapter, okay? Remember, read, then teach, or then access the teaching, and then start your problem sets and that kind of thing. So again, the overall theme is Monday, Tuesday, we're getting done with our reading. Wednesday, Thursday, maybe Friday, we're working on our problem sets, but throughout that time, we should be asking questions, watching the lectures, that kind of thing, all right? So atoms, molecules, and ions. So let's start with just the atomic theory of matter, all right, which basically stems from Dalton's concepts. It's the idea that the fundamental building block of matter is the atom. Remember, before him, you had the Aristotle's 4 elements, right? The earth, wind, air, and fire. And way back a long time ago, Democritus talked about atomos, which is where we get the word atom. But as far as what we're going to cover in our class, we're going to start with Dalton, okay? So Dalton's 4 precepts are there on the left. They didn't all turn out to be true, okay? But most of them were well thought out. They gave us a good starting place, okay? So let's look at those in a little bit more depth. First, he said that all elements are composed of atoms. And building on that, he said that atoms of a given element are identical to one another in mass and properties. But atoms for a different element will be different in mass and properties. Now, this is not actually true, all right? So we're just going to kind of grab a pen here and write a word. Oh, maybe. There we go. Isotopes, right? So hopefully you remember isotopes from last year, which are elements that have different numbers of neutrons, okay? So atoms that have different number of neutrons but are the same element. So in fact, if I had, say, carbon 14 and I have carbon 12, they're both carbon, but they're not the same in terms of mass. So he wasn't quite right there, but it was a good place to start. Remember, science is all about testing hypotheses, right? The next thing he said was that the atoms of an element are not charged, are not changed into atoms of different elements by chemical reactions. He said that, they're not created or destroyed. In other words, they're just rearranged. And this is important, all right? They're not changed into atoms of a different element, all right? There was a prevailing thought at the time that atoms could, if there were atoms, that they would change into different atoms when they underwent a chemical reaction. It's not the case. The atoms rearrange, they become combined in different arrangements, but they don't become new elements, all right? They don't become different atoms. And finally, he said that atoms of more than one element combine to form compounds, which, hey, that's true. And given compounds always have the same relative number of atoms. And that's, where we talked about the law of definite proportions or constant composition, right? And I do want to point out, just on this last slide, that actually in normal chemical reactions, this is not true, this is true. But in transmutation reactions or radionuclide reactions, radioactivity, atoms do actually change into different elements. And in fusion in the sun, or fission in a nuclear bomb, you can actually change an element into a new reaction or into a new atom. So he was close, good place to start, but that was it. It was a good place to start. Now, because he says here that compounds always have the same relative number and kinds of atoms, it makes sense that the total mass before and after a reaction should not change, right? Because those elements are not becoming new elements, right? When they undergo a chemical reaction, they are simply rearranging. So the total mass is not going to change. Most of his atomic theory was actually based on this law. There's another law called the law of multiple proportions, all right, which says the mass ratios in different compounds, if they have the same elements, are going to be some ratio of small whole numbers. We would not expect to see like a formula that looks something like this, right? If we saw N 2.3301.7, we would be like, that doesn't make any sense, all right? We expect to see something like N203 or whatever it ends up being, right? We expect small whole numbers, all right, as far as our ratios, okay? He predicted that law, okay, Dalton did. And he also kind of drew from that something that's obvious, but that it's at least worth stating. If you have two compounds made of the same elements, they're not going to have the same number of atoms. So, for example, if I have, let's say, Fe2O3, right, an iron oxide, I'm not going to find Fe4O6. This thing's not going to be real. It won't work. And that's why last year we talked a lot about reducing our ionic compounds, right? This thing's not going to be real. It's just two of those, okay? So good points from Dalton, right? Now, kind of wrapping him all together, moving on. Basically, he said, look, there's nothing smaller than the atom. That turned out to be wrong, all right? We need to look at electrons. We need to look at radioactivity. We need to start talking about neutrons. All of those things, though, he didn't know anything about. So given what he knew, it was a good place to start. The next thing that's discovered are the electrons, right? And they were discovered using the cathode ray tubes, okay? J.J. Thomson gets the credit for that discovery. And basically, all right, this is another kind of example of a cathode ray tube. He was able to prove that the charge mass ratio of the electron was this number here. And if you know the charge mass ratio, then if you know one, you can figure out the other, right? And that's exactly what Robert Millikan did. So Robert Millikan figured out the charge on the electron in 1909, okay, because he could solve for it, right? So just like we saw, so I know this might be new, so let me kind of illustrate. Density is the mass volume ratio. So if I know the density and I know the volume, I can solve for mass, right? Density is the mass volume ratio. So if I know the mass and I know the volume, I can solve for the density, right? So if we are looking for a charge mass ratio for the electron, if we know one, we can solve the other. So we wanted to find, or he wanted to find the charge. He found the charge using this oil drop experiment, which we talked a lot about last year, and he used it to calculate mass, all right? And they would then find the mass and use it to calculate the charge, and as long as they lined up, they knew they had done a pretty good experiment. And radioactivity is also something we talked about last year, also something that was discovered about this time. The first person to ever observe it was Henri Becquerel. Marie and Pierre Curie studied radioactivity. Marie Curie actually her and her husband discovered radium and polonium. Okay, and throughout their studies, what they were showing was that the nucleus of the atom was spitting out a particle. It was giving something off. That's what spontaneous emission means right here. Okay, so we're spitting out particles. Okay, and the problem is when you start spitting out particles, you start destabilizing your nuclei, and if the nuclei gets too unstable, it will actually come apart and decay into something else. So if it can decay into something else, then it must be divisible. So radioactivity is pretty important there. 3 types of radiation were discovered by Ernest Rutherford. This is the same guy that did the gold foil experiment we talked so much about last year. He found alpha particles, beta particles, and gamma rays. Remember that when we write alpha particles, it's 4-2 helium in a nuclear notation, and it really is just a helium nucleus. Okay, the beta particle is 0, -1 e. It's an electron. Okay, it's basically an electron. And gamma rays, we just write 0, 0, and a gamma. And it is a ray, right? It's just energy. Now, he calculated their charge by passing them through these two charged plates, basically like magnets. And the ray that bends towards the positive is the beta ray, which makes sense because it's negative. The ray that bends slightly down towards the negative is the alpha ray because it's positive, and the one that just goes straight through has no charge, and so it's gamma. All right, that's how we named it. Now, about 1900, if you asked a science teacher or a chemist or a chemistry student to draw a model of the atom, this is what they would have drawn. Right? It's the plum pudding model from J.J. Thomson. It has this positive sphere of matter, which had a positive charge, and scattered around the surface are these corpuscles, these negative electrons, okay, these negative regions. This was disproved by that gold foil experiment we just talked about, where Rutherford shot these heavy alpha particles at this really thin sheet of gold and wanted to see what would happen. So in theory, if the plum pudding model was the actual thing, then the atoms would be stacked very close together like this, just like a wall. And this would be a solid thing. So as the alpha particle came towards it, it would hit it and bounce off. And we would expect to, like if we set up a ring of detectors, we would expect to find all of our detectors of the bounced off particles, right, coming back away from the wall. So here's our origin, or yeah, you get the idea. Right, origin, can't spell today. And as it shoots these alpha bullets, they're all bouncing back off the wall. Yeah, well, that's not what happened. What actually happened was most of them kept going through. We can see in this picture that the majority of our detection points are coming through the gold foil like bullets passing through smoke. And he did find that some of them every now and then would come back, all right, which indicated to him, number one, that Thomson's model wasn't right, and number two, that the middle must be really, really dense, okay? And then there must be electrons going around outside the atom. But that space between where the electrons were and where the nucleus was just empty. He also found that atoms were to be very, very small, between 1 and 5 angstroms or 100 to 500 picometers, okay? So 1 angstrom is 1 picometer, and this symbol right here, that is an angstrom, right? So angstrom. All right. Anyway, Chadwick then goes on to discover the neutron. Rutherford's given credit for the proton. Thomson is given credit for the electron, and so there are 3 main discoveries. Now, a couple things we need to make sure to remember from last year about subatomic particles. Number 1, protons are positive. We normally abbreviate them P+. Electrons are negative, E-. All right. Neutrons are neutral, so we usually go N0. That's how we abbreviate them. Protons and neutrons essentially have the same mass, okay, about 1 as far as AMU. Because the electrons are so small, we pretty much ignore it, right? You can see down here on this chart, these are the AMU of a proton and a neutron respectively. So there's our proton, there's our neutron. Our electron is 5 times 10 to the negative 4th relative to these numbers. So in AMU, very, very small. When we talk about AMU, we're using that to talk about the scale of the atomic level, right? So even the heaviest atom is still 4 times 10 to the negative 22 grams. It's tiny, okay? So we use this AMU, right? And this is an important conversion factor right here. This 1 AMU. We usually round it at 1.66, so it's common in calculations to see 1.66 times 10 to the negative 24th grams for an AMU, right? And we could use that in any kind of, say, like dimensional analysis conversion, right? We would just use that as a conversion factor. So something like that would be how many AMU are in, we'll say 2 grams, right? So 2 grams, well, I know that 1 gram is equal to 1.66 times 10 to the negative 24th grams, right? And I'm sorry. Wow, I made a mistake. 2 grams, where 1.66 times 10 to the negative 24th, wow, I was getting ahead of myself there, grams is equal to 1 AMU. There we go. Grams cancels because it's on the bottom. That's why it's always a good idea to make sure your units cancel. I'm left with AMU. I would divide and I could get my conversion. Okay, sorry about that. Moving on. When we're trying to measure these atoms, right, because they are so small, we use mass spectrometers in order to calculate their mass, okay? And we always compare it to carbon-12. Carbon-12 is just kind of the base mark that we use, all right? So this is a picture of a mass spectrometer. It uses accelerating grids, which speed up our particles as they go through the spectrometer. It uses a magnet to bend them, all right? And based on the difference in masses in the particles, the magnetic field bends them a certain amount. So you can see that this chlorine 37 here, its path as it comes around the bend takes it to a different place. And there's just this one little slit that allows a certain path to go through. So in this case, the chlorine 37 is ruled out, and we only detect chlorine 35. We can compare the amount that we put in to the amount we're detecting and figure out what percentage by mass that chlorine 35 is. Then we adjust the slit, and then we can pick, or we adjust the magnet, and we can pick up the different paths of heavier or lighter isotopes as they move through the mass spectrometer. Now we do write most commonly in nuclear notation when we're starting to get into these descriptions. So remember, this is nuclear notation, mass number on top, atomic number on the bottom, and then just the symbol of the element. The atomic number, the atomic number is abbreviated Z. That's what we call it. The mass number is A. Okay. When we do that, we're often talking about isotopes. All right. So an isotope is an atom of the same element with different masses. You can see down here on this table, we've got carbon 11, 12, 13, and 14. And you'll notice that, you know, the number of electrons is the same. The number of protons has to be 6 because it's carbon, but the number of neutrons is going to change. So remember, mass number, which is A, is equal to the number of protons plus the number of neutrons. So carbon 11, there is my mass number, there's A, and it would be 6 plus 5. So 6 plus 5 equals 11, and sure enough, that checks out. All right, so that's just a quick review of isotopes. All right, let's talk a little bit about atomic weight, and then I'm going to say, hey, take a break. All right, so atomic weights, we're going to use off the periodic table, right? In order to calculate the atomic weight, we take the sum of the mass of the isotopes multiplied by their fractional or decimal percent abundance. So remember, we did this last year. If you have, I'm just making one up, so these numbers probably won't work, but let's say I have 48% abundance of hydrogen. No, let's not say hydrogen, let's say carbon. Carbon 12, and to have 2% abundance carbon 11, and I have 2.5% abundance carbon 13. Oh, 13. And what's that leave us with? I don't feel like it's late. It is late in the afternoon when I'm making this video, and I'm going to use a calculator just because I don't want to mess this up. So 100% minus 48 minus 2 minus 2.5. So I have 47.5% of carbon 14. All right, now these are not accurate by any stretch of the imagination. These are not the real abundances. Okay, but remember, we take the sum, right? This sigma right here, this means sum. Okay, so I would say 12 times 0.48 plus 11 times 0.02. Remember, I'm converting a percent to a decimal, so I need to move it 2 places. Plus 13 times 0.025 plus 14 times 0.475. And I would add that all together, right? Sum those products, and that would tell me the average atomic mass, right? The average atomic weight of carbon. Now, again, okay, I'm just going to say this is inaccurate because I made those numbers up, all right? This is inaccurate, my example, all right? That is how we do that, okay? So hopefully you remember that from last year. Now, we're halfway through this slideshow. If you need to take a break, take a break. If you haven't read past this point, read past this point, right? Read, then watch. So give me 1 minute. I'm going to go grab some coffee. I'll be right back. I'm going to leave it running in case you need to catch up on notes or something like that, but I will be right back. Okay, we're back. Let's talk about periodic table. Hopefully, you picked up last year that our good buddy periodic table super important. All right. Just as a quick review, okay. Number one, it's a system that organizes the elements based on periodically repeating trends. Okay. Remember that there are groups that go up and down. There are periods that go left and right. But when we talk about the groups, remember that's a column. If you're in a column or you're in a group, you're in a family, right? That's another name for the up and down column. But you share chemical characteristics because you have similar, well, identical valence electron structures, okay? Going across are the periods. So you can see here, going this way, this would be the second period all the way across, right? So all between those two arrows would be the second period. Going down here, this would be a group. Remember, the F block is not included in the groups, right? Like nobelium, which I think is number 102 right there, is not a halogen. Okay, so nobelium is not a halogen. These don't go that way, right? But that's where we show. We talk about periodicity, which means repeating patterns, because when we start to like break down the periodic table, right? So we go hydrogen, helium, lithium, beryllium. Okay, so 1, 2, 3, 4. So 1, 2, 3, 4. If we compare that to 9, 10, 11, and 12, so 9, 10, right? Because remember, hydrogen would be roughly right here. 9, 10, 11, 12. Hopefully you remember that discussion from last year. We're comparing those two things. We start to get these repeating patterns. So in this case, we've got, non-reactive gas, soft reactive metal that's in between a non-metal and then a metal, right? Chlorine and calcium, non-metal metal, fluorine, magnesium, non-metal metal, right? So on and so forth. So we find these patterns all over the place. That's called periodicity. The groups have names, right? Remember your group names from last year. We used them a lot. They'll actually become a little bit more important this year. But the alkali metals are the first group, which does not include hydrogen. Keep that in mind, okay? Second group are the alkaline earth metals. 6A, which is oxygen, sulfur, selenium, tellurium, and polonium are the chalcogens, okay? The halogens are group 7A or group 17, depending on how you want to count it, right? That's fluorine, chlorine, bromine, iodine, and astatine. Group 8A or the group 18 are the noble gases, right? Which hopefully you know where the noble gases are. Remember that there is a staircase on the periodic table. To the left side of that staircase are the metals, right? So here's my staircase, right there, the step-like line, right? And to the left, I find my metals, and to the right, I find my non-metals, and around that staircase, I usually find my semi-metals. So things to keep in mind: metals are usually They have luster. Okay, they're shiny. They conduct heat. They conduct electricity. Okay, they have solidity, or they're solid at room temperature, with the one exception being mercury, right? Mercury is number 80 right there, Hg. Mercury is a liquid at room temperature. Now, on the right side of our periodic table are nonmetals. Note that in this picture, nonmetals are green. Hydrogen is a nonmetal. That's usually what we classify it as. And so it's not on the right side of the staircase, but the rest of them are. Okay, they are usually solid at room temperature, but they don't have to be. Like the halogens are gases at room temperature. The noble gases are obviously gases at room temperature. Some of them can be liquids. Bromine is actually liquid at room temperature. So I guess not all of the halogens are gases at room temperature. Iodine is actually a solid at room temperature. I have some iodine. We looked at it last year. It's those purple crystals in that vacuum sealed tube that I have. So unlike metals, which are all but one solid at room temperatures, the nonmetals have various forms that they can be. Okay, they are brittle. They don't conduct heat well. They don't conduct electricity well. They are obviously opposite of the metals. Now, along the line are the semimetals, and in this picture, they're purple, that kind of real like lavender color there. And they're called semimetals or metalloids, right? And they are sometimes like metals, sometimes like nonmetals. They make good semiconductors. Some of them are poisonous, like arsenic is poisonous. So they are the bridge in between metals and nonmetals. Remember our formulas, okay? If you see a subscript after an elemental symbol, that tells you how many there are. So like when we look here, we have O2, that tells me there are 2 oxygens bonded together, right? That's what that little subscript right there means, okay? If you have hydrogen peroxide, you have H2O2. This is not to be confused with a coefficient, right? So if I have 2 C2, whoop, let me fix that there, C2H2, right? This means I have 2 ethynes. So C2H2 looks like this, okay? In this case, I have a coefficient out front, so I actually have 2 of them. Okay, so no, remember, I'm not going to say no, I'm going to say remember the difference between a coefficient and a subscript, all right? Don't forget your diatomic molecules. One way you can remember that is Brinkelhoff. So Brinklhof. Brinkelhoff is a mnemonic, right? It's just one way to remember the 7, 1, 2, 3, 4, 5, 6, 7 of the diatomic molecules. It just means that when we find them out in nature, there's always 2 of them. So you're never going to see Br by itself. It's always going to be Br2. If you're planning on a career that involves medicine or chemistry or something like that, these are going to be really important when you get to organic chemistry, that you remember who is a diatomic molecule, okay? Another way you can remember it is on the periodic table. You have hydrogen over here on the left, and then you have, is it nitrogen or oxygen? Yeah, it's nitrogen first. So you have nitrogen, oxygen, fluorine, and you have chlorine, and then I think it's bromine, yep. Bromine, and you have iodine. So it actually kind of makes 7, which there's only 6 in there, and it says, hey, remember, look over here at hydrogen. So however you remember it, okay? Hopefully you remember from last year the empirical formulas versus molecular formulas, okay? Empirical formulas are just reduced. Molecular formulas are not reduced. Remember, nonmetals, when they combine, are always given in molecular formulas. You should always use empirical formulas for ionic compounds that are always reduced. Another kind of formula we'll actually end up looking at a lot in AP Chem is the structural formula, which is the Lewis diagram we learned how to draw last year. We'll talk about, the Lewis dot diagrams and all a little bit later on. You don't have to draw a structural formula in 3 dimensions. Okay, that's not what that shows. That's called a perspective drawing, right? And we did talk about those in first year chem. Excuse me. Remember that a wedge coming out of the page, all right, means that the molecule is coming towards you. The dash line here, this dash line means it's going back away, and the flat lines mean the bond is in the plane of the page, so it's flat on the page, okay? We will look at ball and stick models. We will see space filling models. Both of those are in your textbook. Ions, again, review from last year. Your ions are elements when they have a charge, so they either gain or lose electrons. Something worth noting, hydrogen can be a positive or a negative ion. All right, it's one of the things that makes it special. When it is a positive ion, it's usually associated with acids, right? But it can be a negative ion. Notice the trend here. We have in the first group, all these guys are +1. Here, these guys are always +2. We've got +3. This is plus or -4 typically, but not always. Then we have -3, -2, -1. And the noble gases don't form ions, so we don't even give them a charge, right? Cations are positive, anions are negative. Normally, we find our anions over here with our nonmetals and our cations over here with our metals. Just to refresh you, some trends. Remember, atomic radius gets larger as you go down and to the left, as does metallic character. Ionic radii actually kind of splits, okay? The difference being nonmetals are now gaining electrons, so they're getting larger. But carbon, which often likes to be +4, gets really, really small. Right? So it depends on the ion. Don't forget your don't forget your normal charges, right? Your regular charges. Okay, things like NH4 are usually, or your ammonium ion is always +1. So your polyatomics are going to come into play here. Because we're in AP, I am going to expect you to learn a couple more about common charges. So things like copper is pretty much always +2, iron's always +3. Mercury is usually +2, lead's usually +2. They don't have to be. I know they're transition elements, but we will learn the common charge that we find on them. The fluoride ion is one that we talk about a lot, the halogens being those negative ones. We will probably use cyanide enough for you to memorize that it's Cn-1. Acetate is an important component of acetic acid. It was on that reference sheet I gave you guys last year. So in addition to some of the polyatomics, these ones that are here in bold, we will probably use them enough for you to memorize. So look over this chart, make yourself a little note. And again, in bold are the ions we use the most. Speaking of ions, remember that ionic compounds are formed between metals and nonmetals. Big key term here is the transfer of electrons, okay, via electrostatic attraction, okay? We only write empirical formulas for ionic compounds. When we do write those formulas, remember we use the cross-charge method. So take the charges on the two ions, flip them to the bottom, make them subscripts, and drop the charges, okay? You need to remember to reduce. If you're doing inorganic nomenclature, right, if you're talking about writing the name for a non-organic compound, write the name of the cation. If it's a transition element, don't forget to put a Roman numeral in there. For the anion, for the non-metal side, change the ending to IDE unless it's a polyatomic. So as an example, all right, actually, hold on. As an example, if we had something like NaCl, this is sodium, and then chlorine becomes chloride. If I have a polyatomic, so let's say something like calcium carbonate, CO3, I would say calcium, and then because I have a polyatomic, I just write the polyatomic. So I don't change the ending on the polyatomic. There are some new things we'll learn about in AP, which you'll see in your textbook. I'm not going to go into great detail on them because, again, we did actually talk about them last year. If you were in Miss Balcom's class last year, you may not have. So I threw a slide in here on 8 and 8. So Nitrate is NO3. Nitrite is NO2. Ite means there's one less oxygen. So this works for the oxyanion compounds. There's also prefixes like hypo and stuff that I will show you in a handout. It's not something you have to memorize. It's just something worth knowing. I'm going to let you read this slide. This is not something you have to memorize. This is just a pattern. If we were in class, we would actually draw it out on the board. But because I don't have my board and I've got a small space here, I just put it in as an image. So basically what we want to look at here is the fact that the central atoms on the second row don't go higher than 3 oxygen. But those in the third row can go up to 4 oxygens. And if we look at the charge, it's going to increase from right to left. So over here, I've got a -1 charge, then I've got a -2, then I've got a -3. Okay, so I'm increasing my charge that way. That's an example of periodicity. Now you'll notice it doesn't hold true, right? I'm looking at the bottom row here for these charges because there's nothing here, right? If we then look at the top, we go from -1 to -2. So we're still seeing the charge increasing, right? That it's becoming a greater charge. I guess you could say the charge is actually decreasing as far as absolute value, but I'm pointing out the number next to the charge is increasing right to left. Okay, so that's just an example of periodicity. It's not something you need to memorize. It's just something worth looking at. Here's the slide I was talking about on hypo and per, ite, and ate. Again, not something you have to memorize, all right, but we'll use it quite often. So just familiarize yourself with the naming convention. So again, ite means one less oxygen than 8. So chlorite is ClO2 minus. Chlorate is ClO3 minus. Notice the charge does not change. Hypo as a prefix means one fewer oxygens, all right, or the fewest oxygens than ite does. So hypochlorite is ClO minus. There is just one oxygen. If you see per and 8, it means one more than 8. So perchlorate is ClO4. Whew. Okay, so that's a whole lot of me reading. Let's look at what that looks like. Up here in our picture, we have a couple things, right? We have, they're going right to left. So we have ClO4 minus, and then we have ClO3 minus, and then we have ClO2 minus, and then we have ClO minus. So I have hypochlorite, I have chlorite, chlorate, perchlorate. All right, so we're just looking at adding something each time. All right, we're changing one thing. So familiarize yourself with that. Not really hard to get a grasp on. It just sounds really complicated when I'm talking to you guys on a video and there's no one here to like throw out an example. Okay, so familiarize yourself with that and we'll use it a little bit. Almost done. Moving through acid nomenclature from last year. This was the last thing we did before we went on break. If you were in my honors class, if you had Miss Balcom, I hope you guys got to it. If not, this slide is really important. First, you have binary acids, and then we have oxy acids. Binary acids are 2-element acids, so like HCl. To name them, we use the prefix hydro. We change the ending to ic. So HCl becomes hydrochloric, HBr becomes hydrobromic, HI becomes hydroiodic acid. You get the picture. If you have an oxygen in your acid, you have what we call an oxy acid. You're going to be able to spot them because normally it's hydrogen and then some polyatomic ion that has oxygen in it. So if you get one of those and the anion, the polyatomic, ends in ite, we're going to change the ending to OUS. If the anion ends in ate, we're going to change the ending to ic. We never use hydro as a prefix for these acids. So we could have HClO, which before was hypochlorite. Now it's an acid, so we say hypochlorous acid. Ite became OUS at the end. If we had chlorate, right, which was our ClO3, right, we would, or sorry. If we have chlorite, which is ClO2, because that's the next example, we would say chlorous acid. ClO3 was chlorate. So when it becomes an acid, 8 becomes ic. So we just say chloric acid. ClO4 was perchlorate. So now it becomes perchloric acid. So just trying to marry this slide here with acid nomenclature there. So familiarize yourself. We don't need to memorize it just yet, but we are going to use it. So hopefully you'll work towards memorizing that naming convention. Promise we're almost done. All right, remember, if you need a break, take a break. We have all week for you to look through this, okay? Nomenclature for binary compounds. This is for our non-metals, all right? Use the prefix system. So if I have CO2, I would say carbon dioxide, because remember, you never use mono on the first element, okay? If I had C2O2, I would say dicarbon dioxide, right? So check out this slide. Always change the ending to IDE, okay? If your prefix has an A or an O and the name of the element begins with a vowel, then you just stick the two together. So dinitrogen pentoxide instead of this, right? Because this would look weird. We don't do pinto oxide. That's bleh. So just cut one of them, put them together, all right? When we're talking about organic, we will look a little bit closer at organic. I'm actually going to upload a different video for that. This is just a brief kind of overview. If it's an organic chemical, we use our organic naming system, okay? The simplest hydrocarbons are going to be alkanes. They're these that you see on the screen. Use the prefix. So meth, eth, prop, bute is 4. And then you just pick up with the regular prefixes from this slide right here. So right on this slide for organic, just so you have it. So we would use meth. So this is orgo prefixes. Meth, eth, prop, bute. And then we keep going down with these, okay? So memorize meth, eth, prop, and bute for 1, 2, 3, 4, and you can add that here. When you start adding functional groups, okay, we do change the ending. So if you have an OH group, that's an alcohol group, that goes from methane, so CH4 would be methane, to methanol. So alcohol changes the ending to OL. We'll talk about a couple of those, but again, this is not an organic chemistry class, so we're not going to talk about a whole bunch, all right? So that is the whole video for the second set of slides. Now, let me quit sharing so we can talk. I know that's a lot, all right? I get it. That's a 40-some-minute video. So might even end up being longer than that. Take breaks as you do this stuff, right? Use the Cornell note system. You know, just like you chunk the reading into 10 pages, or you know, your homework into problem sets, chunk the videos, okay? Read for a bit, watch for a bit, take notes, take a brain break, whatever. Stay on top of your schedule. When you have questions, not if, when you have questions, because I know you will, email me, all right? Make sure that we're checking in on office hours. Take advantage of these resources, okay? So I'll see you guys in the next video. And if you have questions, again, I can't stress this enough, send me emails, all right?